Great, let's look at this question. This is an old question from a diploma exam many years ago. So let's see what they're asking. So we have an X-ray photon. It has a wavelength of 2.000 times 10 to the minus 10 meters, and it collides with a stationary electron. Okay, the scattered X-ray photon has a wavelength of 2.049 times 10 to the minus 10 meters, and it returns along its initial path. So we got the photon coming in, scattered photon going back. So we can kind of see that this is a backscattering, which means that angle of scattering is 180 degrees. So we've been asked to analyze this. We want to determine the momenta of the incident and scattered photons, the magnitude of the scattered electron's velocity using conservation momentum, verify the collision's elastic, and state the physics principles used. All right, we have a lot going on. So I'm going to number these. I'm going to say the first bullet, we'll call that 1, we'll call this 2, 3, and then 4. So first off, if we want to find the momentum, P equals mv is not going to work for a photon. But we have been given wavelengths, and we also know from de Broglie's formula that P is equal to h over lambda. We can use this information. So for the incident photon, we know it has a wavelength of 2 times 10 to the minus 10 meters. So again, Planck's constant being a constant, these sig digs don't actually, or these digits don't count for significant digits. So these 4 sig digs are what's actually going to matter for significant digits. So let's see what we get. So we're going to get about 3.315 times 10 to the minus 24 kilogram meter per second. Now, this, and the other thing I should probably mention, it's not talking about magnitude. I should probably, because I'm dealing with a vector quantity, assign some positive convention. So I'm going to call this rightwards direction positive, and then we'll call this leftwards direction negative. So what that's telling us is that this incident photon has a positive momentum, and then this scattered photon is going to have negative momentum. So the final momentum, or sorry, the scattered momentum is going to be negative h over lambda. I'm going to put the negative there again because it's going left. So this is going to give me negative 6.63 times 10 to the minus 34 joule seconds, and then we have that 2.049 times 10 to the minus 10 meters. So I'm going to get a negative value for my momentum, again expected because this is going to the left and we've called right positive. 236 times 10 to the minus 24 meters. Alright, we have done our due diligence in getting the momenta. So we have been asked to determine the scattered electron's velocity using conservation of momentum. So conservation of momentum is going to say that the momentum initially is going to equal to the momentum after the fact. So before the scattering, after the scattering. Good news with this one. It's a strictly 1D problem. We don't have to worry about trig and all that fun stuff. So that's good for us. So what that's telling us is that the momentum of the photon before the collision plus the momentum of the electron, it's going to be equal to the momentum of the photon after the collision, so we'll put that prime, plus the momentum of the electron after the collision. Now, and I should put my vector arrows over this. So the electron is initially at rest, so it's not going to have any momentum. Now, my electron, I want the momentum of the electron. I want to find the speed of the electron, the velocity of the electron after the fact. So I want to find its momentum. So PE prime, it's going to be the momentum of the photon before the collision minus the momentum of the photon after the collision. So we have a negative there, but we got to be really careful because we're going to subtract this from the negative. So we're going to do this minus this, but we have that negative there. So we have to be really careful with our negatives. So we have the initial photon's momentum, that piece here, and then we're going to subtract off of that this contribution of the momentum going to the left after the collision, hence our negative here. Oh yeah, and I don't know why I wrote meters here. This should be kilogram meters per second. Same thing here, kilogram meters per second. So this is going to give me the momentum. So we are going to get something along the lines of about 6.55 times 10 to the minus 24 kilogram, or I need to 4 sig dig. So I'm going to about 6.551 times 10 to the minus 24 kilogram meters per second. So that is the momentum of the electron after the collision. We also know that P is equal to mv. So if I know the momentum of the electron after the collision, speed, or the velocity is just going to be the momentum divided by the mass. So we got that 6.551 times 10 to the minus 24 kilogram meters per second. We're going to divide that by the mass of the electron. And what are we going to get here? We are going to get, we're going to get about 7.191 times 10 to the 6 meters per second. So this is going to be the magnitude of the electron's velocity after the collision. That was a lot of work. Now, and we're still not even done. We still have a part 3 and a part 4. So part 3 has asked us to verify that the collision's elastic. So when we talk about collisions being elastic, we're looking at the energy before and after the collision. So the energy of the photon before the collision plus the energy of the electron before the collision, and then we're looking at these energies after the collision. So EP photon and then E electron after the collision. So we know for the we know first of all the kinetic energy of the electron before the collision is going to be 0 since it doesn't have any momentum. It's not moving, so it doesn't have any energy. So we know the energy of the photon. We know it's just going to be PC. We know that EP after the collision is also going to be PC. So we're going to use the momentum after the collision times C. And then the electron, its energy is just going to be half mv squared. Now what we want to do is we want to check both sides of this equation. So we need to plug in all of the values that we know. We're going to check, is this equal? Because we know for an elastic collision, the energy before the collision has to equal the energy after the collision. So before the collision, we have this momentum. And we're going to multiply that by 3 times 10 to the 8 meters per second. So this is going to be my E. We're going to call that E initial. So this piece, I don't know what I'm doing here for spacing. I'm going to call this E initial and this E final, just to make life easier. So if I calculate my initial momentum based on, my initial energy, I'm going to have, it's about 9.945 times 10 to the minus 16 joules. So I want to calculate the second part. This final energy, it's going to be the momentum after the collision. We don't need the negative because we're dealing with energy, and energy is a scalar, so we're not dealing with the negative. So we're going to have that momentum of the photon after the collision plus this half energy of the photon and half mv squared. So we got a lot going on here. So if I look at this final energy, ooh man, we do have a lot going on here. Alright, so let's do this. Then we're going to plus 0.5 times 9.11 e to the minus 31 times this squared. So I'm going to get about 9.943 times 10 to the minus 16 joules. So my energy initially and my energy final, they're very similar. You'll notice they differ in that third decimal place. You know what? It's close enough. Why is it not exact? Well, keep in mind, the mass of the electron is not exactly 9.11 times 10 to the minus 31 kilograms. There's more decimals. The speed of light is not exactly 3 times 10 to the 8 meters per second. It differs ever so slightly, but that difference in the third decimal place is pretty inconsequential for us. So yeah, it's close enough to being elastic. So we're just going to say EI, it's close enough to EF. So yeah, we're just going to say it's elastic. And again, that has to deal with accuracy. So we have to state all the physics principles that we used in the problem. Well, we used conservation of momentum to actually find the electron's speed. So in this case, we used physics principle number 4. The second one is more subtle, but anytime you use P equals h lambda, P equals h lambda is physics principle number 9, that wave-particle duality. So at the end of the day, in this problem, the two physics principles that were used, physics principle was number 4 for conservation of momentum, and then wave-particle duality, number 9. So this is a very advanced problem using Compton scattering and conservation of momentum and all that lovely stuff. We can make this slightly more difficult by doing a 2D version of it, which we're going to do next.